Okay, linearization and differentials. First of all, here we should know in this section the most important thing is how would you find the derivative of an inverse? This formula shown as 1 is very important. If we have a function f, and if f is differentiable, and say the derivative is never 0 on an interval that's given, then f inverse is differentiable at every point in the domain. Okay, let's explain. And how am I going to find it? Actually, there's a simple formula. The derivative of the inverse function at the particular point P is 1 over the derivative of f evaluated at f inverse B. So this is really nice. It's the reciprocal of the value of f prime at the point f inverse B. Very nice. This is the reciprocal. We can also see it like this. The derivative of the inverse at B is 1 over the derivative of f at f inverse B. Okay, this is a nice expression we use. Let's see. And I'm going to show some examples about that too. We can directly apply that formula we have found. Okay, I'll give some examples on that too. Then we have linearization. The function that we deal with, f, is differentiable at x is equals to a. Then we have this linearization function Lx. Lx is f of a plus f prime a x minus a. Okay, where does it come from? Actually, this comes from the tangent line equation. Okay, what does it mean, linearization? First of all, let me introduce you. This L is the linearization function, approximation of f at a. Sometimes it's called standard linear approximation or linear approximation of f at a. And a is the center of the approximation. Okay. So why do we need that? Actually, we have an approximation of f by a linear function here. L is a linear function, like ax plus b. Okay? F could be complicated function. So this is a linear function. So why do we do that? So we have a function f, we have a linear function, and around some point, which we call center of approximation, around a, these two functions are taking similar values, very close values. Okay, why do we do that? The reason is dealing with linear functions is very easy. Therefore, instead of dealing with difficult functions, we just say, hey, I'm going to do an approximation and I'm going to find a linear function that could act similarly like f in a neighborhood of this a, and for the values of x that are close to a, I can find the value of f by just using this linear function ax plus b. I mean, this simple. I'm telling you mx plus n. Let's say mx plus n, a linear function line equation. And where do we get that? We get it from the tangent line equation. So this is actually on the right hand side. It's the tangent line equation at a. Okay, we just call it Lx. So everything is actually reasonable. Maybe some pictures, let's see. So this is my f, and this is my tangent line L, right? And I'm interested in some values that are close to a for f. So let's pick a number here, let's say k, close to a, and I want to find f of k. But f of k, maybe f, if you don't have a calculator or a computer, it's going to be very difficult to find f of k. But linearization says, don't worry, use the tangent line equation because they are very close to each other. Do you see? This blue one, which is f, and the tangent line equation, tangent line, they are very close to each other around a. So instead of using this f of x, you can use this L of x around a, very close to a. So you're gonna say f of k is approximately equal to L of k, okay? And it's all to it. That's the idea of linearization. For example, in this example, square root of 1 plus x. So whenever you have root functions, it's difficult to calculate. It's difficult to find the value of it. So it's always good to find the linearization approximation, linear approximation, okay? So in this case, we are interested in linearizations at x is equal to 0 here, and linearization at x is equal to 3, okay? And we can find it, we just find the tangent line equation at this point, and we can find a tangent line equation at this point, and we say, if you're interested in, for example, 0.001, f of 0.001, what you should do is you can put it in here, 001 over 2 is 0.005 plus 1, okay, 1 plus 0.005 is the approximate value of f of 1, f of 0.001, right? That's how you could do it. Like, for example, since we know this linear approximation here, let's say we are interested in f of 3.001, what you could do is, you have the linearization function, instead of x, you can put 3.001, divide by 4 is easier than taking the square root, okay? This is going to be 8.001 over 4, and you get an answer. But if you use this one, it is very difficult. Like square root of 1 plus 3.001 is going to be 4.001 square root. How would you find square root of 4.001, right? This is difficult. Okay. See, it is showing you here. Look, around 0, they are almost the same. So the red one is the tangent line equation, and the blue one is the original function. Look at them, how close they are. Around 0. Look, around 0, they are very close to each other. This is a magnified view of the computer, okay? See, then you get this square root of 1.005 is approximately 1 plus 0.005 over 2. And square root of 1.05 is easy because you're going to just use 1 plus 0.005 over 2. Okay? So it's very close to the true value. This is the true value, this is the approximate value. Look at them, how close they are. This is the approximate value, this is the true value. Very close to each other. Approximate value, true value. Very close. So, don't worry and do the approximation to get closer values. Here, they ask about the linearization function for cosine x near pi over 2. You're going to just find the tangent line equation. You take the derivative of cosine, negative sine x, and evaluate at pi over 2. Negative sine x, sine pi over 2 is negative 1. And here is the slope we got. And then you can find this point by just putting in a point in there. So it is easy. And then we have another notion which we call them differentials. Differentials, you can consider differentials as variables. So to start with, f is going to be a differentiable function. And dx we consider as an independent variable, dy is a dependent variable, dy depends on dx you can consider. And dy is called a differential, and we have such a relationship, dy is equal to f prime x dx. But this comes from, actually, if you remember Leibniz notation, dy dx is equal to f prime. So it comes from it. We call it differential because sometimes we use it. Okay. Here it just tells you the differentials a little bit more. What's the differential? Differential actually, what is dx, what is dy? Here they are trying to explain it to you. Okay. So here this is our curve, and this is the tangent line, and tangent line at the point A. We just move a little bit towards right, dx much. So this distance, actual dx, the differential that we call dx is close to delta x. And what is dy? Dy is just a little bit different. It's not going to be delta y. Delta y is just f a plus dx minus f of a. But this is going to be dy actually, f prime a dx, right? So we don't use delta y, but we use this distance. Okay, so this picture actually shows although delta x is the same as dx, dy is not the same as delta y. Dy is just a little bit different, okay, as delta. That's what it shows. Okay. Alright. But that's all to it. We are going to solve some problems on this. Thanks for listening.